In this statistics lesson, we will be discussing a few additional topics in probability and counting, so please feel free to press pause and read through today's objectives. Okay, the first thing we need to discuss is, does order matter when you're arranging items? And the answer is yes and no. Sometimes it does and sometimes it doesn't. So if you are arranging orders and the arranging items and the order does matter, that is called a permutation. So if I look at the letters A, B, C, if you're looking at a permutation, that means ABC, ACB, BAC, BCA, CAB, and CBA are all 6 different unique arrangements. So those are the 6 permutations of the letters A, B, and C. Now, if you're looking at a combination, this means that the order doesn't matter. So those 6 letter arrangements of A, B, and C would all be considered the same thing because they all have an A, they all have a B, and they all have a C, so it doesn't matter what order they're in. The easiest way to remember the difference between these two is that permutations have position. So like if you're getting nominated for a president or a vice president or a secretary or a treasurer of a group, when you get elected for president, that's important because that's a position, and so the order matters. But if you're on a committee and there's 5 people on the committee, it doesn't matter if you're the first person who's put on the committee or the 5th person. You're on the committee, so it doesn't matter. So permutations go with position, combinations go with committees where the order doesn't matter, just as long as you're on the committee. So when you are doing a permutation, there's something that you need to learn mathematically that's called a factorial. That is n with the exclamation mark after it. What n factorial means is you're taking n, whatever number n is, and you're multiplying it by every integer underneath it. Not every integer, every whole number underneath it. So if I asked you to find 6 factorial, it would be 6 times 5 times 4 times 3 times 2 times 1. If I was asking you to find 4 factorial, it would be 4 times 3 times 2 times 1. And it's also important to note that 0 factorial is equal to 1. Most calculators have a factorial button, so it might be a good time to press pause and get out your calculator and find that factorial button and practice typing in 6 factorial and 4 factorial and see if you get the same answers that I have on the screen. We will be using our calculators quite a bit for permutations and combinations, and so getting to know your calculator and how it can do these things is going to be very important for you. All right, so the objective of the 9x9 Sudoku number puzzle is that you're filling in the grid so that each row, each column, and each 3x3 grid contains the digits 1 through 9. All right, so if we look at that problem by itself, how many different ways can the first row of the blank 9x9 grid be filled? So pretend it's blank. How many different ways could I fill in that 9x9 grid? Okay, so I've got 9 spots and I've got 9 numbers. So if you look at the first spot, that could be any of the 9 digits, and then the next spot could be any of the 8 that are left over. So what you're actually doing is you're finding 9 factorial. Right? The first spot would be 9 options, the next spot would be 8, 7, 6, so on and so forth until all 9 positions are filled. So that would give you 9 factorial, which, as it turns out, there are 362,880 ways that you can fill out a blank line in Sudoku. So just so you know, that's why they can create so many different puzzles. All right, but most permutations require that you are doing you're looking at 2 things. Like you have 4 officers that you're trying to elect for your club, and you've got 7 people running for those 4 positions. Okay, so that's where we have to look at NPR. So N is the number of people who are running, and R is the number of positions that you have available. On your calculator, many calculators have an NPR option. It just depends on where you find it. So I would definitely press pause, take a moment, maybe Google for your calculator exactly where that is so that you know how to use it. Otherwise, you will be forced to use this formula, and that can be, some calculators might get overloaded because the numbers might be too big. So if you have the opportunity, get to know your calculator. take the extra couple minutes and figure it out. All right, so let's find the number of ways that we can form 4-digit codes where no digits repeat on the 0 through 9 keypad. All right, so we have 10 digits to choose from, right? 0 through 9, and our R is 4 because we want 4 spaces, 4-digit codes to come up with. And these codes, the order does matter, right? Because we want distinct 4-digit codes. So this is a 10P4 problem. So if you didn't have that button on your, if you can't find that button on your calculator, you can put it in just like that, 10P4. You would have to do 10 factorial over 10 minus 4 factorial. So that would be 10 factorial over 6 factorial. In this case, 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So notice this whole 6 factorial will end up dividing out, and really all you have left is 10 times 9 times 8 times 7, which gives you 5,040 different ways that you could come up with that 4-digit PIN. Now, this isn't really necessary. Again, you can put this in your calculator and then go right to the answer. But you have to know how to use your calculator. Otherwise, you would have to show the formula like I just did with all the work. All right, if you had 33 race cars that are starting the Indianapolis 500, how many ways could the cars finish first, second, and third? All right, so in this case, our N is 33. We have 33 cars, and our R is 3 because we have 3 positions. So I would just take my calculator and do 33 permutations of 3. Now again, if you didn't have that, then you'd have to use the formula 33 factorial over 33 minus 3 factorial. So that would be 33 factorial over 30 factorial. All right, so 33 factorial is 33 times 32 times 31, and then it would be 30 factorial after that. So I'm just going to leave it written as 30 factorial because those 30 factorials will go away. So really in the end, all I have is 33 times 32 times 31. So that would be 32,736. And again, if you had the calculator that has that permutation option, then you can just write that. So I know that that's what you put in your calculator, and then you can go right to the answer. All right, sometimes you have to have what are called distinguishable permutations. A great example of this is when you're doing a survey. Have you ever taken a survey where you answer the questions and you're like, I feel like I've answered this question once before already. I feel like I've answered this 2 or 3 times already. They just had it worded differently. The news is they did. They do that on purpose because they want to make sure that the wording of the problem or the survey question isn't leading you in any way to answer it in a certain way. So we have to have a way to divide out all the times that I have repeated a question. So you do that by doing n factorial, which will be how many questions you have on your survey, and then you would divide it each time by how many times you had a question that was repeating. So let's do some examples so I can show you how it works. All right, so a building contractor is planning to develop a subdivision, and the subdivision consists of 6 one-story houses, 4 two-story houses, and 2 split-level houses. Okay, so how many distinguishable ways can the houses be arranged? So first of all, we know there's going to be 12 total houses that are going to be in this subdivision. Okay, our N1 is going to be 6 of those one-story houses. They all look the same, right? So but they're going to be scattered in different places throughout the subdivision. We're going to have an N2, which is our 4 two-story houses, and then our N3 is going to be those 2 split-level houses. So those are going to be the same, but again, we're going to put them in different places. So how many ways could I do this but have, notice all those 6-story houses are going to look the same, all the 2-story houses are going to look the same, and the split-level houses are going to look the same. So what you do is you take 12 factorial, and you're going to divide that by 6 factorial, by 4 factorial, and by 2 factorial. And again, if you have a calculator, it's great. If not, that you can put this in with your factorial buttons and get right to the answer. But if you don't, then you'd have to write everything out. So I'm going to focus on 12 factorial and 6 factorial because I know 12 times 11 times 10 times 9 times 8 times 7, and then 6 factorial will be left. So that 6 factorial will get rid of that 6 factorial. Okay. Then I can look at 4 factorial. Now, 4 factorial, so let me write my numerator again. Okay, so there's my numerator. All right, 4 factorial is 4 times 3 times 2 times 1, and 2 factorial is 2 times 1. So I can start looking for other ways that I can simplify out numbers. So like 4 times 2 is 8, so 4 times 2, that 8 will divide out that 8. And then 3 times 2 is 6, and 6 goes into 12 twice. So you can start just kind of like mixing and matching to get everything taken care of. But when you are done, you will end up with 13,860 distinguishable ways that we could arrange those 12 houses so that they're all in a different order each time, and you don't have exactly the same layout. So that one would come in handy if you're doing a survey. So like you had, so this would be the same thing. You had a 12-question survey. 6 of the questions were exactly the same. We just worded them differently. Another 4 of them were exactly the same, but we worded them differently, and another 2 were exactly the same. So we really only had 3 questions on the survey, but we were asking it to you in different ways so that we weren't trying to lead you to answer it a very specific way. That's kind of how that would work. All right, if you're looking at combinations, this is where the order doesn't matter. What you're going to do is use this formula, and again, your calculator will have this NCR option. N is your option, your how many objects you have, and R is how many you would like to arrange them in. So like 12, you have 12 things, and you want to arrange them in groups of 3. So this is the formula there. Important to note that this is also the same as NPR divided by R factorial. Those are the same. So you may see it written that way as well. But again, note use of your calculator is going to save you a lot of time on these as well. All right, so State Departments of Transportation plans to develop a new section of interstate highway and receives 16 bids for the project. The state plans to hire 4 of the bidding companies. How many different combinations of 4 companies can be selected from the 15? So again, there's no order, there's no specific order, it's just we need to get 4 of them on there. We don't care who's 1, 2, 3, and 4. All right, so this is going to be we've got 16 bidding companies, that's my N, and 4 companies, that's my R. So I want 16 companies, and I'm going to choose combinations of, oops, not R, 4. That should be a 4. Of 4 of them. So that's going to be 16 factorial over 16 minus 4 factorial times 4 factorial. So I can divide out the 12 factorial, right? 16 minus 4 would be 12, so I can divide that out from the numerator. So that would give me 16 times 15 times 14 times 13. And then the denominator would just be the 4 factorial, 4 times 3 times 2 times 1. And again, there's lots of different ways you could put this in your calculator. But again, if you have this NCR option, you can go from here right to my answer, which is going to be 1,820. So again, utilizing your technology in a good way. All right, so that's how you do combinations. Very similar to the way you did permutations, just with that slight difference where you have to divide by R factorial again. All right, so when it comes to counting, we've got that fundamental counting principle that we talked about in an earlier lesson. We have permutations that utilize that factorial option. We've got the distinguishable permutations that we can use, and we also have combinations. So the hardest part for most people is just figuring out what should I use. So let's look for some key words that will kind of let us know what's going on. So a student advisory board consists of 17 members. 3 members serve as the board's chair, secretary, and webmaster. So each member is equally likely to serve any of these positions. Everyone is qualified to be a chair or a secretary or a webmaster. Okay, what is the probability of randomly selecting the 3 members who will be chosen for this board? Okay, so first we have to find how many ways could we do that. So because this is a board, there are very specific positions, secretary, chair, and webmaster. So we have 17 members on the committee, and we have 3 very distinct positions. So this is going to be 17 permutations of 3, because we have 17 people and 3 positions that need to be filled. So that's going to be 17 factorial over 17 minus 3 factorial, which is 14 factorial. So 17 factorial over 14 factorial. So that'll just be 17 times 16 times 15, because the 14 factorials will divide out. So that would give me 4,080 different ways. Okay, so what is the probability of just randomly selecting the 3 members who are chosen to be on that board? Right, so we're going to select the 3 people, and there's only one way we can do that, right? Because there's just those 3 specific people. So the probability of selecting the 3 people that were elected to those positions is just 1 out of 4,080. So a lot of times you'll be using these permutations to find some probabilities. And if you needed the decimal approximation for that, that'd be 0.0002. So you don't have a very good chance of picking the 3 people that were elected out of those 17. All right, here's another example. And again, these are all just showing you different ways that you can apply these probabilities that we just talked about. Find the probability of being dealt 5 diamonds from a standard deck of playing cards. Okay, this one's a little bit more involved. So in a standard playing deck, there's 52 cards, but there's only 13 diamonds. Okay, so let's talk about that first. Playing cards, there's 13 diamonds. The order doesn't matter. As long as we get the diamonds, we don't care which ones they are, what order we get them in. So the possible ways that we could choose 5 diamonds out of the 13 that we have is going to be 13 combinations of 5. We need to know that number first. Okay, so it turns out if you put that in your calculator, that is 1,287. So there are 1,287 ways that I could get 5 diamonds if I just started with the diamonds. But here's the problem. I'm not starting with the diamonds, right? I'm starting with the whole deck of cards. So the probability that you're going to get 5 diamonds is going to be the number of ways that you can choose the diamonds. And so there are 1,287 ways that you could choose those 5 diamonds out of just the diamonds. And then you're going to divide that by the total number of ways that you could choose from those 52 cards, those 5 particular diamonds that you want. Okay, now that number is a little bit more, it's a little bit bigger. That's when you put that in your calculator, it's 2,598,960. So you have to divide the number of ways that you could choose those 5 diamonds out of the 13 and divide it by the number of ways that you could choose those 5 diamonds out of the entire deck of cards. That's way more involved. All right, so this is 0.0005. If you decide to take up poker professionally and play on the World Series of Poker, you are going to start having to study these types of probabilities, because you are going to have to know what's the probability. You know, if I need that river to be a diamond so I can get my flush, what's the probability that I'm going to get a diamond on that next card? And they have to be able to do these kind of mathematical problems in their head. And it's absolutely stunning if you've ever watched the World Series of Poker, how quickly they can do those computations in their head. All right, a food manufacturer is analyzing a sample of 400 corn kernels, and they are looking for the presence of a toxin within that corn kernel. In this sample, 3 kernels. So here's my N, right? I'm starting with 400. And I'm looking, I have 3 of those kernels have dangerously high levels. Okay, we are going to randomly select 4 kernels and see what happens. Okay, what is the probability that exactly 1 kernel contains dangerously high levels of toxin? Again, this is a very complex problem where you can't just do one thing and then you're good to go. Okay, so we have to look at a couple of things. The first thing we have to look at is the possible number of ways that we can choose 1 toxic kernel if there are 3 that are in there. So if I have 3 and I need to choose 1 of them, and it doesn't matter what order it's in if I get 1. So that's just 3. So that's the first thing I need to know. That's the number of ways that I can choose that 1 toxic kernel out of the 3 that are toxic. Okay, then I have to look at the possible number of ways that I can choose 3 non-toxic kernels, because I'm choosing 4, right? I want 1 to be toxic, and I want the other 3 to not be toxic. So I next need to look at the combinations that I could choose those 3 kernels from the corn that is not toxic, which I know that would be 397 kernels are not toxic, if 3 of them are toxic. And that is 10,349,790. Okay. Using the multiplication rule, I would multiply these 2 numbers together, and that would tell me the number of ways that I would choose 1 kernel and 3 non-toxic. So here's my 1 kernel, that's my 1 toxic, and these are my 3 non-toxic. So I'm going to multiply those 2 together, and that is going to give me a very large number, 31,049,370. Okay, so that's how many ways that I can choose 1 kernel that's toxic and 3 kernels that are not toxic. It's a lot of different ways. All right, and then I have to look at the number of possible ways that I could choose 4 kernels from the 400 to begin with. So my last thing I need to compute is 400 combinations of 4 kernels, and that is 1,050,739,900. Whew. All right, now we have all the information we need to do this problem. So the probability that I get 1 toxic kernel, probability that I get 1 toxic, is the 31,049,370 divided by the 1,050,739,900. Crazy big. Okay, it comes down to, when you put those in your calculator, 0.030. So you have about a 3% chance of picking that 1 kernel that has dangerously high levels of toxin. Again, this is a very involved example. Most examples aren't going to get that crazy, but it's an excellent example of how you can actually look at how these probabilities would be used in manufacturing, because that's you will see that kind of thing if you work, especially in quality control. All right, but betting is one of the best places that you can see. Again, probabilities are all about gambling, so let's talk about gambling. All right, so in horse racing, there's a bet that you can place called a trifecta, and this means that you accurately predict who finishes first, second, and third exactly. Okay, they must be in the correct order. To be a trifecta, you have to correctly get all 3, first, second, and third place. Okay, so first of all, let's see, it says the 144th running of the Kentucky Derby had a field of 20 horses. So if there's 20 horses, how many different trifecta bets could you place that are unique to win the race? So because it is order matters, this is going to be a permutation. So we have 20 horses, and we want permutations of just those 3 places, first, second, and third. All right, so that would be 20 factorial over 20 minus 3 factorial. So 20 factorial divided by 17 factorial, and that turns out to be 6,840. So you would have to place 6,840 different unique bets to guarantee that you would win. It's probably not a good strategy to bet every single one. All right. If a bettor randomly selects 3 horses, so say I just put their names in a hat and I chose 3 because I don't know anything about horse racing. What is the probability of winning by selecting these 3 horses? So these are the 3. You had Justify to Win was the first one, so Justify was the name of the horse. He's going to win. He's going to get first place. Good Magic is going to finish second, and Audible is finishing third. All right, so there are 6,840 bets, and we want just that one to win. Here's the problem. It's not quite that easy. So in a perfect world, if every horse was equally matched, then we would have a 1 chance out of that 6,840. But here's the problem. some horses are just better than others. So you know that there's certain horses that are going to win or that are going to at least place in the top three. So it's not really as simple because all of the different bets, all the 6,840 bets that you could place, don't all have the same probability of working out. Some have a better chance than others. But just so you know, so that in a perfect world, if they were all equal horses, that would be my answer. But if you put your $2 bet on there and you win, you get $282.80. So you could put $2 down, pick 3 horses out of a hat, and if you do win, you get $282.80 back when you cash in your ticket. So might be worth it just to have a little fun and try your druthers and see what happens. All right, so here's the example of that survey I was telling you about. Okay, so pollsters often repeat the question to see if the subject is thoughtlessly providing answers just to finish quickly or if they're really reading the question. So you have a survey with 10 questions. 2 of the questions are identical and 3 other are also identical. Okay, so for this survey, how many different arrangements would be possible of those survey questions? Okay, so in our case, our n is going to be equal to 10 because we have 10 survey questions. Our n1 is going to be 2. The 2 questions are the same. And then our n2 is going to be 3 because those 3 other ones are the same. So 10 factorial divided by the 2 factorial and the 3 factorial. So 10 factorial would be 3,286,800. And then 2 factorial and times 3 factorial, that's 3 factorial is 6, that's 2. So 2 times 6 is 12. And that would give us 302,400. So we could create 302,400 unique surveys with those exact same 10 questions, but in different orders. That might not be practical for you to accommodate every single permutation, unique and distinguishable permutation that we could find. But in a perfect world, you would do that. You would print out every single one, so every single possible combination, permutation was set out. Unfortunately, that's not usually, and sometimes your population isn't even broad enough. So say your college only has 3,000 students. I don't have 302, right? So I can't even come up with that many because I only have 3,000 students in my entire population. All right, another place you can see is the lottery. So Florida's Cash 5 requires, if you win the jackpot, requires that you select 5 different numbers from 1 through 35. And the same 5 numbers must be drawn. Again, order doesn't matter. So this one is a combination. We just want our 5 numbers to get drawn. We don't care what number gets drawn first. Okay, so how many different lottery tickets are possible for every drawing? Okay, so we have numbers 1 through 35, so that's my n. So my n is going to be 35. And my r, I am choosing 5 numbers. So I want 35 combinations of 5 numbers. So that's going to be 35 factorial divided by 35 minus 5 factorial, and then divide again by 5 factorial. So when you put that all in your calculator, that's going to end up being 324,632. So that's how many unique lottery tickets you'd have to put in to guarantee that you win. So what's your probability of winning the jackpot? It's only one of those 324,632 that is going to get you that winning jackpot. And this is why people often call the lottery a tax on people who are just bad at math, because that's not a winning strategy, right? You know you're not going to win. Odds are very much against you to win the lottery. However, it does pay to dream, and if you do have a couple bucks, take a chance, because you can't win if you don't play. So it's one of those things. All right, so speaking of lotteries, let's talk about the Powerball. Okay, so I have some questions here. So I would like you to read through these questions. So press pause, read through these questions, and answer which you think is more likely, which it to become. So just go through each one and circle what you think is going to be the best option, or what you think is the most probable. All right, welcome back. Let's see how you did. Here's the bad news. you're much more likely to do any of these things other than win Powerball. Okay, and I actually have all the odds written down, so if you're curious, these are all the odds. So 1 in 1,500 to become an astronaut trainee, but the odds of winning Powerball is 1 in 292,201,338. So basically, you have a better chance of. I actually had some students that once figured this out. You have a better chance of dying from a shark attack while you're being struck by lightning than you do of winning Powerball. So it doesn't look good. But the good news is we can all dream, right? We can all dream about winning Powerball. And the great thing is if you go on the Powerball website, you can actually see they show you all the math and have all the formulas and everything. So it's nice to see that, those probabilities and these formulas in action on the Powerball website. All right, so that ends our discussion on probabilities. The next time we come back, we will keep talking about probabilities, but we'll talk about probabilities in contexts. And so you might want to come back and hear all about that. So see you next time.